Hello once again, welcome to the third screencast of the school year, in which now we're dealing with equivalent fractions, only this time with monomials. Interesting stuff. Alright, so let's get right into it. You guys know how this works. Here is the problem that I want to show you how to do. During the period 1800 to 1900, 6 out of 23 U.S. vice presidents later became U.S. presidents. During the period 1901 to 2000, 7 out of 21 vice presidents later became presidents. The question is, during which period did a greater fraction of vice presidents become presidents? Well, to figure this out, first we have to create fractions that represent each of the time periods being talked about. 1800 to 1900, as we saw, 6 out of 23 U.S. vice presidents later became presidents. So that's 6 out of 23. In 1901 to 2000, well, as we can see, we had 7 out of 21. During which period did a greater fraction of vice presidents become presidents? Well, it's kind of hard to compare the fractions right now unless we change them a bit so that they have their equivalent fraction form. So in order to do that, we have to find out what each of these fractions are equal to. We have to make two equivalent fractions, but here's the kicker. Both of these new equivalent fractions have to have the same denominator, what we call the lowest or least common denominator. That's right, the LCD. But the nice thing is, calculating the LCD is the exact same thing as calculating the LCM. That's right. So, look at the two denominators. We got a 23 and we got a 21. We have to calculate the lowest common multiple between 23 and 21. All right, so let's do that. You know, that's not so bad if you think about it. 23 we have to create the factor tree for, but if you think about it, 23, looking at our list of prime numbers, yeah, 23 is prime, so you know what, let's circle that one because that one's done. But 21, as we know, is 7 times 3, both of which, of course, are prime. So to find the LCM, all we need to do is factor out both. So 23 just stays as 23, because keep in mind, 23 is prime, and to factor 23 would be 1 times 23, which is really not going to get us anywhere, because multiplying by 1, as you know, changes nothing. So we'll just use 23 itself. But 21, if we explode it out, is 3 times 7. Now notice that there's nothing here to circle. There's no common primes. That's right. So all we have are 3 leftovers. And remember what we do with leftovers? That's right, we multiply them all together. So our leftovers are, in order, 3 times 7 times 23 in order to get our LCM. So 3 times 7 is 21, and 21 times 23, confirm this with me, is 483. Which means our new denominators must each be 483. All right, that's good to know. Which means now we have to figure out what the numerator here will be and the numerator here will be. And to do that, we look to the denominators, because notice how both denominators are quote-unquote full. We have a single number for both denominators. So let's take one at a time. Think about it. How can we go from 23 to 483 using multiplication, using division, what have you? Well, let's see here. Didn't we just kind of figure out that 23 times 21 is 483? Which means to go from 23 to 483, you simply multiply by, that's right, 21. And as we all know, if you do something to the top, you have to do it to the bottom as well. If you do something to the bottom, as we just did, the denominator, you must do the exact same thing to the numerator in order for it to be an equivalent fraction. So we're going to multiply the numerator, 6, by 21. And upon doing that, we get 126. So 6/23 is an equivalent fraction to 126 483rds. All right, so now we're going to figure out what the other numerator would be, the one that's going to be right here, and then we'll be able to compare these new equivalent fractions and have the answer. So 21 times what is going to give us 483? Because whatever that is, we got to do it to the top as well, the numerator. Well, as we just saw, 21 times 23 is 483, so now we're going to multiply this time by 23. And we also have to do it to the numerator. And 7 times 23 gives us, yes, a larger number, 161. So the two fractions that we are now comparing are 126 483rds and 161 483rds, Well, notice that the numerators are, of course, the same, which means to compare the fractions and to find out the answer to the question, which asks, during which period did a greater fraction of vice presidents become president, means we have to look at just the numerators. And of course, 161 is a larger number than 126, so therefore we can safely say between 1901 and 2000, a greater fraction of vice presidents became president. Ta-da! What we just did was we just compared two fractions. And what we did, in order to do that, was we had to find the lowest common denominator. And notice that to do that, we just did the exact same thing as the LCM. Only now, because we're dealing with fractions, we don't call it the LCM, we call it the LCD. But notice it is the exact same process. Okay, keep this in mind as we go into our next problem. And the next problem I'm going to do with you, only this time, there are variables involved. That's right. This one's not a word problem per se. Nope. What we have to do is we have to make two equivalent fractions equal to 2a over 5b and 3 over 5ab squared that both share a common denominator, which means we have to find the lowest common denominator of these two fractions here, which once again, as you just saw, means looking at the denominators, because it's kind of in the name, lowest common denominator. Between 5b and 4ab squared, we have to find the LCM. And we might remember how to do that. To find the LCM of two monomials. Now again, we're just focusing on the denominators here. That's all that matters for right now. We have to factor out each one. All right, so let's start with the numbers. 5. Well, 5 can't factor anymore. 5 is prime, this we know. But 4 can certainly factor. 4 is 2 and 2, each of which are, of course, prime. So therefore, 5b explodes out to 5 times b. And 4ab squared explodes out to 2 times 2 times a times b times b. All right, so now what we have to do is we have to look for, you guessed it, as we've done in the past, common factors. Let's see, numbers. We got a 5, a 2. Nope, no common numbers. Do we have any common a's amongst the two lists here? Here and here? No, I don't think so. All right, well, what about, yeah, b's. We have a common pair of b's. Do we have another common pair? No, we don't. No, wow. So, to find the LCM, but of course in this case it's the LCD because we're dealing with fractions, all we need to do is first include one b from the pair of b's that are up there, but then the rest are all leftovers, so we have to include all of those. We have to include the 5, and the 2, and the other 2, and the a, and that second b. And we have to multiply all of these together. So let's do this. Let's do it with the numbers first. We got 5 times 2, which is 10, and 10 times 2, which is 20. Not so bad. And then we have, let's see, any a's? Yes, we have a single a, which we know is raised to the first power. And then we have 2 b's, so b times b is now b squared. So guess what? We just found the LCM, but again, in this case, it's the LCD. It just has a different name, because we're dealing with fractions, of 5b and 4ab squared. So let's go ahead and throw those up there as our new denominators. We got 20ab squared here and 20ab squared here. All right, we're doing well. Now, just like before, the one with the presidents, notice that we looked to the denominators and we asked ourselves, what can we multiply the first original old denominator, and by old denominator I mean the starting one, 5b and 4ab squared, what can we multiply the old denominator by in order to get the new one? Now this is where the challenge comes in, because now we're not just dealing with numbers. We're dealing with also variables. But the nice thing is, as we have talked about in class, variables are nothing but number wannabes. So treat them like numbers. They want to be numbers so badly, treat them like numbers. Let's start, though, with the numbers that we're familiar with. Here we have a 5 and a 20. How can we go from 5 to 20? What comes into your head instantly? Yeah, mine too. Multiply by 4. But we're not done. We're trying to get 5b to become 20ab squared. So to get 5 into 20, we multiply it by 4. But we have to make this b into ab squared. So let's just focus on the letters now. Look at the a. There's no a over here with 5b, but there is one single a here. So therefore, if we multiply by yet another a, we're going to end up with an a over here. And let's look at the b's now. We got 1b here and b squared here. We have to ask ourselves, single b to the first power, times what is going to give us b squared? So b times what will give me b squared? And you might remember that b times b will give me b squared. So there it is. We have to multiply 5b times 4ab in order to get 20ab squared. All right, let's confirm that this makes sense. 5 times 4 does give us 20. A, right here, times nothing over here will give us an A over here. And once again, B times another B will give us, that's right, this B squared. All right, so we got that. Which means if we multiply the denominator by 4ab, we also have to multiply the numerator by the exact same thing, 4ab. All right, so we'll do that in just a moment. Let's look to the other fractions right here. We've got 4ab squared, and we need to make that into, again, 20ab squared. All right, so we're kind of good on that one. This one's closer than we thought. Let's see here. Let's focus on the numbers. 4 to get to 20. Well, we just kind of talked about that. 4 times, that's right, I'm thinking the same thing as you. 5 will get me 20. Now, what do we have to multiply a by to get a? It's not another a, because if we multiplied a by another a, we'd get a squared, but we're not looking for a squared, we're looking for just a. Ah, yes, times 1. A times 1 will give us a. And by that same rationale, what do we have to multiply b squared by to get back to itself, b squared? Well, again, not b, because if we multiply b squared times a third b, we're looking at b times b times b, which is b cubed. We don't want b cubed, we want b squared, but it already is b squared. And as you know, to multiply anything by 1 keeps its identity. That's called the multiplication identity. Very good. So we multiply 4ab squared times 5 times 1 times 1. What are we really multiplying by? Yes, of course. We don't need those 1s right there. All we're doing is we're multiplying by 5. So of course we can just say this whole thing is times 5. So if we're going to multiply the denominators by 5, we got to multiply both the numerators by 5. All right, so now we're ready. Now that we found out what we need to multiply both numerators by in order to get our new numerators, we're ready to go. Okay, so let's do this. 2a times 4ab. Let's see. Focus on the numbers first. Take it in pieces. 2 times 4 will give us, of course, 8. Let's now look at the a's. A times a will, of course, give us a to the second power, a squared. And notice that we have nothing else to multiply from this numerator, 2a, but yet we still have this b to consider, which means we are just going to throw it in there. So the numerator is 8a squared b. Good to know. Now for the other numerator. 3 times 5 times 1 times 1, but we just said that's nothing more than 5, is of course going to give us 15. Ah, we got it. We got it. 8a squared b over 20ab squared is equivalent to 2a over 5b, and 15 over 20ab squared is equivalent to 3 over 4ab squared. That's how we do it, folks. That's how we do it. That is how we do it. To summarize, here we go, right here. What we did first was we calculated the LCM of the denominators, which we called the LCD. Then we set up equivalent fractions with empty numerators and LCM denominators. Empty numerators, you might remember, were here and here, but the LCM were the denominators. Remember, the LCM was 20ab squared. And then we asked ourselves, what do I multiply the quote-unquote old denominators to get quote-unquote new denominators? And again, we found out that it was 4ab, and over here we thought it was 5. We found out it was 5. And then part 4, the final part, was multiply the old numerators by the same exact factor to get the new numerator. And once we did that, we had a full equivalent fraction with both a new numerator and new denominator. And we were done. Nice job. So what does that mean for you? That means here we have your problem to do. What you're going to do is you're going to create equivalent fractions to 3x over 2yz and 5y over 4xz. Now remember the steps. Here they are again. Same ones we just saw. First, I want you to calculate the LCM of the denominators. Then set up equivalent fractions with empty numerators and LCM denominators. And then ask yourself, what do I multiply the old denominators to get the new denominators? And then, once you know that factor, multiply the old numerators by the same exact factor to get the new numerator, and you are done, okay? All I want in your answer, of course, are your two new fractions that are equivalent to 3x over 2yz and 5y over 4xz. However, they both must have the exact same denominator. And that denominator, as I said, is the LCM of the denominators. All right, so this one's a little bit more of a challenge. I have all the faith in the world of every single one of you 7th graders because you're all doing so wonderfully, and I'm so proud of all the work you've been put in just within the first month of school. Keep it up. You're doing great. If you have questions, feel free to email me. Feel free to talk to me over the long weekend ahead. I'd be happy to answer any questions that you might have. All right? All right. Good luck to you. I know you can do it.